Hi, my name is Hamram Lee, and so this is the 2019 short course for the Thermodynamic diffusion. And then, well, actually, so I had some short course, like the chapters is composed of chapters, the 6 chapters, but that was the recording in Korean, and then this is the English version, and then probably it would be like good for some students or some people working in the industry which is related to the automated diffusion. So let me introduce myself, and my name is Hanbram Lee, and then I'm an associate professor in the material science and engineering department at Incheon National University, Korea, and then and then also I am an associate editor of the chemistry material, the ACS publication. And then if you are interested in my research, the topic, you can just stop by my the group website. The address is very simple, the nanomaterial.kl. Okay, so I used to work in at Stanford University for the postdoctoral scholar in the 2010 to 2013, and I finished my PhD degree in the post-tech 2005 2009. Okay, let me explain so what we need to study to understand the ALD. Probably I assume that all of the students to take this class is the students do not have like strong not very familiar with the ALD, but have like basic the knowledge about like physics and chemistry and electricity, and then some small part of the surface science. And then the course is composed of some fundamental stuff first, and then I will explain the introduction of ALD and then very basic cross characteristics of ALD, and then we move on to the ALD precursor and reactants, and then I also explain how we can set up our ALD system like ALD chamber or ALD tools and ALD apparatus. And then also in the chapter 6, we will take a look at two example which has been used for the silicon device the industry. And then in the final chapter, I will briefly introduce the selective diffusion and a selective etching, which were developed from the ALD process, but that's very the attractive the topics these days to prepare the future the nanofabrication technology. Okay, let's start the first chapter, the review of the fundamentals. I already explained in the previous slide. I assume that all of the student has already basic the background of the physics and chemistry and electronics, something like that, and definitely the mathematics. Okay, so let's take a look at the thermodynamics and then kinetics first. So this is the pipe made with the steel, and then as you know, this pipe is rusted after exposure to the air and then oxygen, and if you leave it like for like 1 week or 2 weeks, probably 1 year, probably we can see a lot of rust on the surface of on the pipe. So as you know, this is the very simple the reaction. So this is the ion. The ion reacts with oxygen, and then the ion, the elements in the steel, that is to change it to the iron oxide. So the color of the iron oxide, it looks like a red light color, the rusted color. So we can see the color change of the steel pipe. So so this is we usually call that this is the oxidation process, which is the very similar to the like a burning the papers and also burning something. But the burning process is very fast oxidation process, but this is a not very fast oxidation process. So we can just think about the two different things on that. And then the first question is, does this reaction occur? Like, for example, so we have ion and then we have oxygen. And then so first question is, this reaction is going to the ion oxide from the ion and oxygen. So the other question is, how fast does the reaction occur? So we know the rusting process is not very fast. Probably we take like at least the few days or probably at least the 1 week to see the formation of the rust. So uh, if you have like question about this, we have to take a look at the thermodynamics. But if you have to take a look at this, we have to take a look at the kinetics. Like, so this is a why very important to understand the ALD process is, so we have a lot of the precursor and the counter reactants. Sometimes our question is, okay, so this reaction between the counter precursor and the counter reactant is taking place or not? Or this reaction is how fast of this reaction? So those both of the questions are probably the main question to the ALD researcher. So we have to take a look at the thermodynamics first. So as you know the basics of the thermodynamics, we have to understand the Gibbs free energy first. The Gibbs free energy can be defined by the enthalpy minus Ts. T is the temperature, the absolute temperature, and then S is the entropy. So we usually call the measure of the disorder for the process which changes the free energy, like for example reaction. So if you have like A is going to B, so this is a final state and this is an initial state. To take a look at this reaction is taking place or not, so we have to calculate the Gibbs free energy difference. So Gibbs free energy difference is Gibbs free energy after reaction and it gives minus Gibbs free energy before reaction. Like we need to obtain the difference between the after and then before, so we can change the reaction. If the Gibbs free energy difference is smaller than 0, so the reaction is is taking place spontaneously. So like for example, this is the energy state. This is a G initial and G final. So, well, definitely, because the energy state of this is the smaller than that, the reaction is going to that. You can just think about if you the rolling down the stone from the mountain, that the mountain is rolling off to the ground. So this is the very spontaneous reaction. If the Gibbs energy is larger than the difference of the Gibbs energy is larger than 0, definitely the reverse reaction will proceed spontaneously. Like for example, so the stone is here, and a stone is not going up to the top of the mountains spontaneously because the delta G is larger than, like actually the energy difference is larger than 0. So, but if you have like a delta G is equal to 0, the reaction is balanced. We usually call that like equilibrium, or sometimes we can call like steady state. So scientifically, the forward reaction is same to the backward reaction. So for the spontaneous reaction, more stable bonding is in the product. So there are the 3 different cases. And then the second is the great disorder in the product. So for example, so if you have like a pure water and if you have a pure ink, and then the disorder, the measure of disorder is not very high, but if you put like pure the droplet of ink into the pure water, that the ink molecule is like a penetrate inside the water, and then that will mix with each other. So this the measure of the disorder should be increased. So greater disorder in the product. So it's quite closely related to the diffusion process, or both. So this is the more like some detailed process how we can calculate the thermodynamic terms, and if you have like these the reaction, So A plus B is going to C plus D. And then this is the free energy change. Well, definitely small a, small b, and small c, small d are the mole number. And then there is the free energy change. Definitely the delta G is smaller than 0. The reaction is spontaneous, or delta G is 0. That reaction is balanced. So this is the so another definition of the G. And then if you have I substance, and then the Gibbs energy of I can be defined by GI0. GI0 means the standard state free energy substance I. So your material or your substance in the standard state, the Gibbs energy of that is a GI naught. And then R is a gas constant, and then T is the temperature, and then AI is activity. Activity could be same to like a pressure for the ideal gas, but for the ideal solution, activity is same to the atomic fraction. So you can just change it. This is the 2. Delta G is the delta G naught plus RT, and then AC AD over AA AB, because you can just calculate that. If the equilibrium state, delta G is going to be 0, so this is a 0, and then delta G naught, that is the delta G at standard state, is same to this. So we usually call that, this is the K. K is the equilibrium constant. Okay, so this is the equilibrium in the two phases. Okay, so phases. So this is the pretty much related to the how we can obtain the vapor pressure of our precursor. Like, well, simply speaking, we need to think about the Clausius and Klein-Paton equation to calculate that. So if you have like a liquid phase here, and there are some vapor phase here, at constant the temperature and constant the pressure, if you pulling out of this the piston, definitely your the liquid phase is changed to the vapor phase to keep the temperature and then the pressure. So we can calculate that. So because that is the constant, the condition, delta G is going to 0. So delta G, delta H minus T delta S is going to 0. So delta H, like enthalpy difference, is same to T delta S. Here, well, like the general definition of the delta H, like the enthalpy can be defined by the system of the energy of the system, and then the pressure times the change of the volume, PV. So this number is same to delta U plus the P delta V. And then let's try to differentiate both sides with respect to the temperature, and then we can eliminate the T, and then this is a constant, the respect to the T, and then dP over dt. So this is the equation, and then dP over dt is same to delta S over delta V, and then delta 2 minus delta 1, delta 2 minus V2 minus V1. And then so this is the definition of enthalpy, that is the delta S. The enthalpy change is same to the L over T, where L is the essence of heat of the vaporization. And then so delta P over delta T is same to L over T times V2 minus V1. And then so also we can also easily change it using the ideal gas law, and then we can change these like P, and then we can change this PV equal nRT. So TP over T D and dP over dt can be written in LP over nRT squared. And then using, so this is L over N, that is the change of the vaporization enthalpy. And we can change this the equation to this. And then for the integration, we just put the P into the left side and T into the right side. and then dP over P, and then dt over T squared times the delta enthalpy vaporization over the gas constant R. After integration, NP can be defined by minus 1 over T times delta enthalpy, the vaporization, over R plus C. That is the integration constant. So as you already recognize that this is some very important equation of the vaporization, like vapor phase, the pressure is as a function of the temperature. So if you have like a 20 degrees C, the vapor pressure is, for example, the P is P1, and if you increase like temperature to like 100 degrees C, definitely the pressure is changing. That the P2, definitely P2 is larger than P1. So to obtain the proper or the enough vapor pressure of, or enough the large number of vaporized our precursor, we have to have some condition for the temperature. So how we can estimate that? So we have to use this equation. And this equation could be simplified y minus ax plus b. So there are some two unknown coefficients, a and b. So that means if you know uh, vapor pressure at specific temperature, and if you know the another vapor pressure at another the temperature, so you have the two equations, you can easily calculate the A and B. I will explain that later. And then this is the reaction rate. So well, this is a kinetics term. So if you have A and B, and then at the beginning actually the number of concentration of A is 1 mole, and then that is the change in 0.6 mole and then 0.2 mole. Definitely that is the change to B, like A is going to be. The concentration of B is increased from 0 to 0.4 mole and then 0.8 mole. So the rate of reaction, how fast? So this is the answer to our second question. The rate of reaction can be determined by the monitor the change of concentration of either reactant or product as a function of time t. So this is the rate because the reactant A is decreased, so the sign is minus dA over dt minus, or so with the amount of the decreasing A, which is the same to the amount of increasing B, so we can define the rate is the dB over dt, but there are no minus sign here because there is an increase. So let's take a look at the example. So this is the N2O5 is changing to N2O2 plus the O2. The reaction rate is dN2O5 over dt. Definitely we have to multiply 1 over 2 because there are some coefficient in front of each terms. And that is the same to the product. So this is the one product and a second product. So well, you already know that the reaction rate can be rate constant K times concentration A and then concentration B. But there are some reaction order M and N. So will be determined by the coefficient. So if you have like this, the reaction, because there are coefficient is 1 and 1, the rate can be determined by K and NH4 plus times N2 NO2 minus. So this is the reactant concentration and a reactant concentration. You have to keep in your mind the rate, to obtain the rate, we only have concentration of reactant. We only consider the concentration of the reactant. So overall reaction order is 1 plus 1 is 2 because we have 1 and 1 here. So this is the reaction. If you have like if you consider the reaction which the phase transformation of A to B, and then the rate can be defined by dA over dt minus, that is the same to Ka by the reaction law, and then change the sign here in an integration, and then by this integration you can obtain this. This is the A concentration of A as a function of the time t, and then this is the A naught, that is the initial concentration of A. K is constant and then t is the time. So so this is the like you can just easily not E minus KT. If you plot this curve, it looks like this, right? Exponential decrease. You can just think about the concentration from A is decreased very fast, but like because the concentration, the A is changed to B, concentration of B is increases very fast. So to obtain that, well, we know everything about that, like A naught, and then we control the temperature, we measure the concentration, but we don't know the exact number of the K. To obtain the K, so you can change the equation to logarithm term, and then you can just plot it, and then this slope is the K. So this is the very typical way to obtain the rate constant. So this is the activation energy and an Arrhenius plot. There are two different reactions. The first one is ectothermic, like we released a lot of the thermal energy from the reaction, and then the endothermic. So the reaction is taking place. So we need to obtain some more thermal energy to give the reaction. So the reactant is A plus B, and then the product is the C plus D. Typically, the reaction is going to like that, but there are some energy barrier. We usually call that is the activation energy barrier. So A plus B is changed to something. We call that the activation complex, and then going to the product. So this amount is the activation energy barrier, and then this is the reaction barrier. And then this is the exact different case. A and B is going to activated complex. This is the activation energy, and then the change is C plus D. The reaction energy difference is this amount. So the Arrhenius plot this is the reaction constant. K can be defined by A, this is a coefficient, E exponential minus EA over RT. So this is this number. If this number is very large, the K constant should be decreased very fast. So we call that this is the activation energy barrier. So how we can obtain that? We just change this equation to the logarithm term. So this is the EA over R. That is the slope. Once you plot 1 over t versus ln k, and then you can obtain this linear plot, and then you can obtain the slope, and then you can calculate, because you already know the number of the gas constant, you can easily obtain the EA. Okay, let's move on to the vacuum. So why we need to use vacuum? What is the vacuum? So this is the vacuum cleaner. Food saver using the vacuum. This is a bulb. To prevent the oxidation of the filaments, we have to use the vacuum condition. This is the vacuum tubes that would used to be used for like some electronic the system before the transistor. So this is the sucker and used in the bathroom, and then this is the blood container. So you definitely have some experience if you try to analyze your blood. You just the nurse is collecting your blood and put into this container, and there are some blood here, and then she removed this to prevent any change of your blood. So why we need to use the vacuum? So probably some of the students or the people have some experience to put like protection film on the smartphone to prevent any scratch on that. So probably there are a lot of the particle maybe you can just see some bubble inside this the protection film. That looks like a very I'm not very satisfied this. So, but anyway, so human it's actually scientifically very dirty stuff. So we continuously generated a lot of the dust, and then these dust making some defects on our semiconductor process or ALD. You just trying to handle some very tiny gas molecule and then gas molecule counter reactants. Definitely, this particle is much larger than that one. So you have to remove the particle inside the reactor. So that is the reason why we need to use the vacuum condition. Okay, let's take a look at what is the pressure first. So this is our Earth, and our because we have the gravitational force, we have the atmospheric the layer, and then there are a lot of gas molecule here, and the air is composed of almost 80% of the nitrogen, 78% of the nitrogen, and then 21% of oxygen, and then 1% of the argon or neon or some small amount of the gas molecule. So the pressure can be defined by P is the force over unit area because we stand here and then so on your head we have like this amount of atmosphere, oxygen or nitrogen or some other gas molecule, you can just feel like some pressure on your head. So that is the pressure on the Earth. So how we can measure the pressure? And so this is an experimental setup for the Torricelli, who is the very famous Italian the physicist, and he was curious about how we can measure the pressure of the air atmosphere, and he put some mercury into the cylinder, and he just flip it up. He put that mercury into the beaker, and he measured so this height difference. Well, definitely because mercury is not very light, that is very heavy. Mercury is going to down due to the gravitational force, but so this space is going to change the vacuum. This force is going down, but the air, some force from the atmospheric pressure is definitely push this mercury is back to the upright the direction. So definitely this force and this force is balanced. So he trying to measure this height because uh, this height can represent the amount of the atmospheric pressure. So he measured that. So this height is a 60. No. This height is 67 centimeter. So well, actually, so this height is almost the same in any other the different side of the cylinder because the pressure can be defined by the force per unit area. That means the force per unit area are same in the any other the places. So there are three different the units to call that one. So typically the 1 Pascal is same to 1 Newton per 1 square meter. So this is the SI unit. This is the SI unit used in over the world. And there are some other one. 1 bar that is the same to 10 to the 5 Pascal. And then 1 atm that is 1 atmosphere. And then that is the same to 1.0173 times the 10 to the 5 Pascal. So the 1 atm that is the balance the column I already explained that, and he measured the 76 centimeter for the atmospheric pressure. So because of that, we use some unique unit millimeter Hg because he used the mercury, and then this is the 76 centimeters into 760 millimeter. So we usually use the torr for that. 760 torr for 1 atmosphere. So sometimes we need to psi, pounds per square inch. That is the 14.7 psi. But this is used for the vacuum, like a lower pressure. Usually this unit used for the higher pressure, like the regulator in the gas bottle. You can see the psi unit. So, okay, what is the pressure actually? So the pressure is the sum of the gas molecule, the momentum transfer. There are a lot of the gas molecule, many gas molecule. Gas molecule generate like making collision on the wall. So, well, the pressure is definitely coming from the collision. So the gas pressure is momentum transfer of the gas, the molecule. To calculate the pressure based on the microscopic scale motion, so we set this box. There are some gas molecule here. The gas molecule is going to flying to like this way, and then sometimes maybe have some collision on this surface. So the first of all, the traveling distance of the gas molecule, the speed of the gas molecule is Vx. We only use the one dimension. And then the Vx bar, that is the average velocity of gas molecule, and then delta T, this is the traveling distance. And then number of molecules striking wall, that is the 1 over 2, N. N is gas molecule concentration, how many gas molecule per unit volume. And then this is the distance, and then A, area. So this term is going to volume. And then N, that is the number of molecule per volume. So N times V is changed to total number of gas molecule, which makes collision on the wall. But we have to use the 1 over 2 because there are some two different ways. And then number 3, the momentum change of the one collision. So because the one momentum is the mv, and then going to this way, and then reflected back to. So the momentum change is the mv minus mv. So it's going to 2mv. So the total momentum change is, this is the total, the gas molecule, and then momentum change per unit, momentum change per molecule. So this is the total momentum change. And then AVX bar squared delta T. So this is the total momentum change. Well, as you know, the force is the change of the momentum. You can just differentiate of this, one prime. And then so you just delete the delta T. So this is the force. And then the pressure is the force per unit area. Pressure. This is the force. And then divide by A. Remove A. So this is the pressure. So we only consider the one-dimensional A-axis and the x-axis. So to change the three-dimensional, you can use this equation, and then the pressure can be defined 1 over 3 N mv bar square. So this is the pressure calculated from the microscopic scale. So this is the, using the ideal gas law, we can change the pressure with the nRT over the N. Well, you can just think about the pressure depends on the how many molecules inside this volume. And the pressure depends on the how heavy of the gas molecule inside this space. How fast of your molecule, so that affect the pressure. So we already expected that. So let's think about the mean free path. So we have a lot of the gas molecule in the space, and that gas molecule is having the random motion, then makes a lot of the collision with each other. So mean free path means, so this is the very cloudy screenshot in the Gangnam Station in Korea, probably maybe the Friday night. So the mean free path is very short because if you just think about you can just work in this very crowded the street, you can make a lot of the collision with other people. So this is the like almost like I don't know, maybe 6 a.m. in the Gangnam street and there are no people. Maybe the year like the collision, the number of collision is very low compared to this. So mean free path means the mean free path average distance between the two different collisions. So very high, very small. So definitely high pressure, many molecules, the mean free path is very short. But low pressure, small number of molecules, the mean free path is very long. So how we can calculate the mean free path? So we have gas molecule here and a two making collision. So the other molecule is should fly inside this area. So if the diameter of the gas molecule is d, the effective collision area is going to be pi d squared. And then this is the volume, and so we have this effective collision area volume, and then this is the traveling distance of the gas molecule v bar t, and then this volume is pi d squared v t. So mean free path means how many like a number of collision uh, in unit volume. Because of that, the mean free path is the v var t over pi d squared vt and v. That is the number of the gas molecule uh, per unit volume. So this is the mean free path. And then there are the average, the relative velocity can be defined by the root 2 v var and an effective volume of the target strip. We already calculate this. So this velocity is changed to delta 2 v var. So the mean free path is transformed to, well, we usually call the lambda for the mean free path. That is the change it to that. So you can also change it to using this the ideal gas law. So this is the simple form of the mean free path. So simple form, or you can just more simplify this form. Mean free path unit is a centimeter. Mean pressure is torr. So this is a simple calculation. If you have 1 atmosphere, mean free path is almost a 20 nanometer. It's very small, very short. It's like Friday Gangnam Street. 1 millitorr mean free path is almost a 5 centimeter. It's not very short. It's pretty long. Let's think about the 10 to the minus 9 torr. Probably that is the typical the pressure in the XPS or the surface analysis tool. The mean free path is the 50 kilometer. The gas molecule cannot meet any other different gas molecule inside the chamber. So that sounds like a very like interesting. And then we need to think about the gas impingement on the surface. So how many gas molecule impinge on the surface? So we define the gas impingement flux pi, and then the measure of the frequency in which molecule on or collide with the surface. But definitely high pressure means the high impingement flux and a short the mean free path, and a low pressure and a small number of impingement rate, and then the longer the mean free path. And then so the number of molecules that strike the element on the surface perpendicular the coordinate the direction. So you can usually calculate this, and well, let's just think about the final the result. So impingement rate is proportional to the pressure, and then, but inversely proportional to the molecular mass. Okay, so this is the final stage, the characteristic contamination time. So that means, well, we have very clean surface, and we are very worried about, or we are very interested in. So how long does it take to cover all of the precursor molecule on our surface? That is the characteristic contamination time. characteristic contamination time is how long would it take for the surface to be covered by one monolayer of the molecule, like for example the precursor. So that definitely inverse of the impingement rate. So this is the characteristic contamination time equation. So that is the inversely proportional to the pressure. Okay, let's try to calculate that. If the sticking coefficient is 1, that means if you put like 10 molecule, and then if the sticking probability is 1, the 10 molecule make one collision, 10 molecule adsorb on the surface 100%. But if your sticking coefficient is like 0.5, the 50% of the total molecule can adsorb on the surface. So the characteristic contamination time for 1 atmosphere, the characteristic contamination time is the 3.5 nanosecond. It's so fast. Your surface is covered by the oxygen or some other nitrogen once you expose to the air, because there are many gas molecules in the air. For the 10 to the minus 10 torr, the characteristic contamination time is almost the 7.3 hour. It's almost a 7 hour and then 20 minutes. It's a very long time. So at this time, we have to define the exposure. So that is developed by the Langmuir. And then the exposure means how many molecules can absorb on our surface. That is definitely depends on the time, exposure time, and then exposure pressure. So because of that, one Langmuir can be changed to 10 to the minus 6 torr second. That means if you have like 10 to the minus 6 torr oxygen and you expose like 1 second, so 1 second, and then your substrate is exposed to 1 Langmuir. Okay, so plasma. Plasma is very important things for ALD as well as like CVD or sputtering or any other semiconductor process. The plasma is the fourth state of material. So you can just think about the solid and then liquid and then gas. Increasing the thermal energy, increasing the temperature, the gas molecule or the molecule is getting the larger amount of the energy. That is the change from the solid to the liquid and liquid to the gas. If you put the more energy onto the gas, like using like electric field, so that gas molecule is split into the two parts. That is the ion, positive ion, and a negative electron. So we call that is the plasma. So interestingly, the plasma is it's as we can see the plasma in outside of the plasma, we believe that is the neutral because the total number of ion, total number of electron are same. But inside the plasma, you can see there are some uh, the positive ion here and a negative electrode here. So the well inside the plasma that is not neutral anymore. So the ionized gas with the equal number of positive and a negative charge is consists of the neutral atom. So how we can make the plasma? There are two different ways. So definitely we need to put some more energy onto the gas phase. The first of all, we just heat it up, the heat of gas. We call that is the thermal plasma. Almost we need to heat up like 4,000 K or 20,000 K, very high. But more practical way is the arc discharge. We just apply the electric field. So this is the thermal plasma, and then we do not use this technology anymore, but that is the PDP. We use the plasma for the display technology. This is the neon sign. Definitely use the plasma. So why we need to use the plasma? So, well, actually, for the semiconductor process or ALD process, that should be like conducting under the vacuum condition. Like, as you know, the vacuum condition is isolated system. So there is no way put more energy into the vacuum inside. One good way is just to heat it up. We just heat it up and then we just give the more thermal energy. But That is not enough. So how we can apply, how we can put the more energy into like the vacuum condition. So as a consequence, actually, the plasma is generated, plasma is formed inside the vacuum condition. So this is quite same. So in the space, well, there is a screenshot of the gravity. So Sandra block. And then, well, so if you think about you are in the space and you just wearing like a space suit, so there is no way to transfer your energy to the outside. So as you know, well, in this gravity, the movie, so like conversation is taking place using like electrical signal, not the sound, because there is no way to give the voice, the energy from your voice to the other. And then we have the very isolated system. There is no way to energy using like, well, so this is the some screenshot of the movie actually. So he has some special the ability to give the more energy to the other, but that is not possible. So we need to use the other. So that is the plasma. So take a look at what happened inside some plasma state when we apply the electric fields. What happened inside the vacuum tube? So this is the neutral. This is the neutral, the gas molecule, and then we apply the electric field, and then electron is going to the gas molecule, and then the gas molecule making the collision, and then that also generated another electron, and then that is well, the original electron is going to fly the other way. So there are definitely the other neutron molecule here that makes some another the collision. It looks like it's a chain reaction. So this is the Townsend discharge. So electron making positive ion, also generating one more electron, and those electron making some positive ion again, so generating a lot of the electron. So that is the Townsend reaction. So this is the reaction. So how we can calculate the total number of the charge currents from this discharge. So this is the discharge current that is defined by initial current, and then exponential alpha d, that is the distance between two electrons. If this electrode is very far, so the discharge current should be very increased. And then this is a coefficient, and then this is the emission coefficient. Well, definitely this discharging current definitely depends on what kind of molecule we use and how large is the electric field. So the breakdown, we need to take a look at the breakdown. So if you increase the electric field and more and more and more again, definitely, uh, uh, this the discharging current is increased. That is almost infinite. That is the breakdown, like a direct current formation from one electrode to the other. So that is the breakdown current. So critical breakdown field and voltage can be defined by using this. And then this is the voltage for the breakdown. And then that is as a function of pressure. And then D is like a distance between two electrons. We usually call that is the Paschen law. And then this is the breakdown voltage. And then this is the PD. PD means if the PD increase, that means the pressure increase or the distance increase or both. So that means if you you need to find very low value of the minimum value of the breakdown voltage. To make that, you have to carefully control the pressure of the gas molecule and then the distance between two electrodes. Well, practically, we cannot control the distance to the electrode, so we have to carefully control the pressure. So this is the electron and ion. As you know, the electron is much larger than ion is much larger than electron. The mass of ion is also much heavier than the electron. So this is the mean prepass because due to the size of electron and ion and the size of the mass of electron and ion, for the mean free path for the gas molecule is much, the electron is more like a much faster, have like very fast motion compared to the ion. So the thermal velocity is so fast. So this is the electron, and then this is the ion. So electron can be almost 10,000 times more accelerated compared to the ion. So there are two different types of the plasma. If you apply the plasma, if you apply like electric field, this is a plus charge, but definitely minus electron is going to this way, plus ion is going to minus. So, well, definitely electron is arrive on this surface, and then plus ion arrive on this surface. So this is a DC. So these plus and minus do not change. So electron is going on the surface, ion is going on the surface. If this electrode is not conductive material, that is the insulator, so this electron cannot go anywhere, and then this ion is definitely cannot go anywhere because this is not conductive. So there are electron is piled up, and then there are the plus potential difference between two different electrodes will be eliminated because this is a plus, but there is a lot of the minus here. This is a minus, but there is a lot of the plus here. So if you use like insulating electrode material for the plasma, we have to use the different type. So this is the RF plasma radio frequency. Plus and minus is changed very fast. Plus minus, plus minus, plus minus, plus minus. So this RF plasma frequency is the 13.56 megahertz. That is the RF, the plasma frequency. Because of that, due to this fast exchange, fast alternating the plus and minus in the both sides, so we can maintain the plasma condition. Well, we can use a lot of, well, typically for the plasma in the ALD system, we use the RF plasma. So there are three different types of the plasma system. So this is the CCP type, capacitively charged, capacitively coupled plasma. One electrode, the other electrode, and this is our sample, like for example, wafer. So this our substrate is connected to ground, but our shower head is connected to the plasma generator. So this is the ICP type, ICP, inductively coupled plasma. We have quartz tube, and then there are a lot of coil, and then this coil is connected to RF plasma generator, and then electric field is alternatively changed very fast. Due to this change, there are some magnetic field plus and minus, and then by changing electric field, plus and minus is very fast change. Also, this change of magnetic field, another electric field is generated inside this quartz tube. This generation of electric field also generates plasma inside this quartz tube. So this is the very making very high density plasma inside our system. So there are two different types of plasma. So this is the remote plasma. If you use like a plus ion and a minus electron, that plus ion can make big collision on your sample. To prevent this big collision, that big collision induces some defect formation. So we generated plasma here, and then we just transfer this plasma species onto our surface. We call that this is the remote plasma system. So there are some different electron and an atom interaction. Well, that's the most common thing is ionization. Electron is going to neutral gas ion, and the gas molecule is changed to gas ion, and they change it to the two electron. And also the electron does not kick out the one more electron, but that is moved. This another electron is to the higher energy level. This higher energy level is relaxed again to the bottom energy level, and then that is to release this amount of photon hard. Because of that, we can see very specific color of the plasma, which is depends on the kind of the gas. Like, well, you can see some different colors: ammonia plasma, or oxygen plasma, or hydrogen plasma. So this is a dissociation. Electron is going to compound, and then that is breakdown. This compound is breakdown, but this is not ion, but that is the very unstable species. We usually call the radical, and this make very high chemical reactivity, which is very useful for the etching process, or like plasma in the ALD system. There are some different type of the electron and atom interaction. Okay, let's think about the wettability. So this is the movie of making the film on the uh, plate. Well, that is the cooking process of the crepe. But you can just think about, to make like ALD film, you have to think about the ALD film should be very uniform, very uniform. But due to the surface energy, so this is the very difficult, and then we just make non-continuous. Well, it looks like that. The film does not flat anymore, but that is looks like an island. So the reason for this is the surface energy changing. What is the surface energy? Surface energy means there are some atom, like in this is the microscopic scale view. There are some atoms here, and then let's think about this. This atom has the 4 different bonding, but this atom has the 3 different bonding. Because of that, there are no bonding here. This atom is going to inward. This atom has the 2 bonding. Definitely this atom is going to inward. So how we can define the surface energy? So the surface energy means this atom has additionally possessed an additional energy, and we can call that is the surface energy. Well, for example, if you like stand in the 3rd floor, you have additionally possessed the potential energy. So that is the same to the surface energy. So define to do that. So the surface energy, how we can define the surface energy, the energy to move this atom to original position. That is the surface energy. The surface energy gamma can be defined by delta G over delta A. So this is the surface energy. Let's think about the surface energy in microscopic scale. So if you have like this solid, and then cut it out, and then making the 2 different surfaces. So this process in microscopic scale, you just breaking down a lot of the bond between this atom and this atom and this atom, this atom and this atom, this atom, this atom, this atom. You make the additional 2 different surfaces because you just put the more energy, and then the energy you putting into this solid is changed to the formation of these 2 different surfaces. So this is the definition of the surface energy in microscopic scale. So this is the law, that is the surface atom density. How many atoms on the surface? And then epsilon, that is the bond strength. So how strongly the bonded with each other, uh, two different the atom. And then this is the number of broken bondings. How many bondings is broken down? And then we have to consider the 1/2 because we just put one knife. We just used the one knife, but there are some formation of the two different bonding breakdown. So we have the 3 different crystal plane, and then 1 0 0, 1 1 0, and a 1 1 1. So this is the 1 1 1 0 0. This is a 1 0 0, and then this is the 1 1 0, and then this is the 1 1 1. If you already took like some introduction of the material science and engineering, definitely you know the atomic density on the 3 different the planes are different with each other, and then the atomic density of the 1 1 1 is much larger than the other one. So let's take a look at. So this equation is changed to 1 over 2, and then the bracking bonding is a 4, and then 2 over a squared. A means like the unit cell, the constant, and then the final value is looks like that. And this is also the final value, also final value. The the surface energy of one on one is much smallest value compared to the other. So large one and large and the smallest one. Well, you can just think about if you have, because you have the uh, many surface atom on one surface, because of that the surface atom on the one surface, it feels like a very stable because you have a lot of friend on the surface. So your atom on the one surface, it feels like a very stable, but in 100 surface, your the atom on the surface does not feel like a very stable because there is no friend. So that is the surface energy in the atomic scale. So the surface energy is pretty much important one. Well, also the surface to volume ratio to do some nanotechnology. So in the bulk case, so the ratio of the surface atom is pretty much small compared to the interior atom. But with decreasing the size, the surface portion of the surface atom is very large. It's very increased. Like for example, if you have the 1.2 nanometer of the nanocrystal, your surface portion is the 70%, 76%. That is the too large. So as I told you before, the surface is not very stable. That is the unstable. So because of that, the new nanoparticle want to reduce the surface. So to do that, for that, your nanoparticle is want to agglomerate it with each other to decrease the surface area. So that is the three different example. So this is the glove used for like keys in the winter season, but this is the much warmer than the other like 5 finger style one because the surface to volume ratio is much smaller than this. There are two large surface area here. So this is the wolf living North Pole. So the wolf ear, it looks like a very spherical shape. That is, a surface to volume ratio is small because he or she wants to decrease the heat dissipation from his or her body to survive in very low temperature condition. But this is the wolf, not wolf, actually the fox. Fox is live in the desert, so the temperature of the desert is very high, and then he want to increase the surface area, and then he want to increase the surface to volume ratio. So let's think about the growth of the thin film. I like this one. So this is the window in the raining. On the raining, there are a lot of the droplet here, and then sometimes they make some like continuous growth. And then so this is the freezing of the bubble in very like cold environment. And as you can see, this freezing fragment is connected with each other, and that is changed to the continuous. So that is the very similar to the growth of the thin film. So the small atoms on the surface, and then that is finally meet the other, and then make some like cluster, and a cluster is increased. Definitely cluster already encounter the other one. This is the quiescence, and then after this quiescence, continuous growth is taking place. So nucleation, quiescence, continuous growth. That is the typical process of the thin film growth. So this is the sodium chloride plan view nucleation. There are a lot of the nuclei here, quiescence with each other, and then quiescence cluster is increased, and then finally continuous growth. It looks like a very similar to the window on the in the raining. There are three different growth models. First one is the island or the VW growth. When the atom is cluster more strongly bonded, like the surface energy is very small, and then the surface energy, like this deposit material, is very stable with each other. So they want to put together, not spread out. So this is the island growth. And then the layer by layer growth, the FM growth mode, because the surface energy of your substrate is very high. You deposit material want to cover the surface, and then layer by layer, or layer by layer, or like SK growth mode, layer by layer first, and then change it to the island growth. Layer by layer, and then change it to island growth. That is, as I told you before, you already recognized that. So the three different type of the growth is strongly depends on the surface energy difference between the surface and then your deposit material. So there are like two different nucleation process. So this is actually the sauna, public sauna. There are two different nucleation always are taking place. The first one, that is the homogeneous nucleation. You can see a lot of the vaporized water in the air. That is the homogeneous nucleation. The water is just formed in the air, but there are a lot of the droplet on like window. That is the heterogeneous nucleation. The formation of water is taking place on the glass, not in the air. That is the heterogeneous nucleation. We just think about gas phase, and a liquid phase only. But to consider that, we have to consider gas phase, liquid phase, and solid phase. Solid phase on this glass. So this is the homogeneous nucleation. We have liquid phase. Oh, no, we have gas phase, and the gas phase is changed to liquid phase, like nuclei. The size of nuclei with the radius r, and an energy change by phase transformation. There are two different energy changes. One is this unstable gas phase is changed to liquid phase, so volume change, and also after formation of these nuclei, the additional surface is formed. That is the surface formation energy change. So this is the volume change surface energy phase transformation. 4/3 pi r cubic times delta GV. That is the Gibbs energy change per unit volume. And then delta nu s 4 pi r square, because the surface area of the sphere nuclei is 4 pi r square, and then lambda. So total change of the total change of this system is this. So as you know, this is actually the increase of the surface energy. This is the increase with the order over 2. So this is a decrease of the volume energy. This is decrease order over 3. So the total energy change looks like this. There are some maximum point. So you can just think about your nuclei is increased, and that is increased. If your nuclei is larger than this value, so your phase transformation, your nucleation is taking place, but before that, maybe your nuclei is going back to gas phase again from the liquid phase. So this number is very important. Also, this number is also very important. So we call this R star is the critical size, but larger than R star, stable, nucleation proceed, but smaller than R star, dissolve into the solution again. So we can easily obtain this by differentiating. So R star is number here, and then at R star we can obtain energy barrier, that is the delta G star. That is the energy barrier. It looks like activation energy barrier. Heterogeneous nucleation. So we need to consider solid, and then we need to consider gas phase and then liquid phase. So there are some balance angle. This is the surface. There are one surface, the other surface, and then this surface. Three different surfaces should be considered. So volume change, this is the volume change, and surface energy change. So volume change is obtained this. This is a volume change. Volume for unit volume and a nucleus volume. To obtain this hemispherical cap volume, we need to calculate that. Well, simply speaking, the critical size of nuclei looks like this, and the critical energy barrier looks like that. So the critical size of nuclei and critical energy barrier of the homogeneous geometrical term. So this is the R star and a delta G star of the heterogeneous nucleation. So there are some term here and another term here. That is composed of a lot of the theta or something like that. We call that this is a wetting factor. The theta means the contact angle between this liquid and a solid phase. So you can just think about if cosine theta is like 180 degree. So the cosine is going to looks like that. So that is a minus 1. The cosine 180 is minus 1. There is a minus 1 plus 3 minus 1. And this is going to 0. So that is going to 0. Delta G star is going to 0. So that means this energy barrier is going to 0. There is no energy barrier. So that means your film forms very flat layer, so without any the activation energy barrier. But so the contact angle looks like this is the contact angle, the 180, that is almost a flat. So the other one is almost, this is the 360. Oh, the contact angle is 0. That is the 0. That is 0. So 180 is minus 1. So the one that is the 180. That is the 180. That is 180 is minus 1, and then this is going to 1 for the 180. So the heterogeneous nucleation activation energy barrier is same to the activation the energy barrier of the homogeneous nucleation. That means your nucleation is taking place on your surface, but that is quite actually is taking place in the air. That is the same. But if your surface is very active and then very like surface energy is very high, your the film is formed is very flat. The contact angle is 180, wetting factor is 1, critical energy barrier is same to homogeneous nucleation, but contact angle is 0, the energy barrier. So you can just think about the island growth. Your surface energy balance is this value is the large. This looks like that. Layer by layer growth. That you have the balance between these two different terms. So this is the final part, uniformity and conformality. If you measure the film thickness, you can measure some different the film thickness. So there are some average film thickness. You just add up all of the thickness, measure all the different place, and then divide by the total number of the thickness measurements, and that is the average thickness. Thickness uniformity can be defined by this average thickness, the difference between average thickness from your point and divide by average thickness, and you just trying to measure how far from your thickness from the average thickness. So that means your thickness uniformity number is very small. That means your thickness uniformity is very good. Your film looks like very flat. But the thickness uniformity is very high. Your film is not very uniform, and then your roughness is very high. So this is the some conformality, the definition. First of all, aspect ratio, called that H over W. So if your hole or trench is very deep and high, and then your aspect ratio is increased, and then side or step coverage, So you have thickness T on the top, and the sidewall, the thickness is S. So this is a sidewall step coverage. Like for example, 95%. So your thickness is almost same to the sidewall thickness. And the bottom step coverage means B, bottom thickness over the top thickness. So as you know, the conformality is very important. The advantage of the ALD. So we have to keep in our mind. So what is the aspect ratio and what is the conformality? How we can measure the conformality?